Hello, welcome to Maths with EJD. In this video, I'll be solving a two-part question, with the first part being this. We have the A part, which is this: prove that the space, Q, the space Q of rational numbers, is not complete. In fact, the not is in capitals, is not complete. Okay, so can we try to unpack this question? You want to prove that the space Q of rational numbers. A rational number is a number that can be expressed as the ratio of two integers. So if you can put one integer over another, that's a rational number, right? So Q is one rational number over another, one integer over another integer. So we want to show that it's not complete. And if you remember the definition of completeness in one of the previous videos I did, if you check under this playlist, you will see that we say that a metric is complete, right? If you take a sequence, in that space, and then that sequence converges to something within the same space, right? That's the idea of completeness. Okay, so let's take this now. So we want to prove that the space Q of rational numbers is not complete. Okay, so in this case, you actually need a particular sequence. You need a particular sequence, and you want to show that the sequence is a sequence of rational numbers, but then the sequence itself does not converge to a rational number. So that way you can show that it is complete. So let's take this particular example. Say this. Okay, so to show that the space Q of rational numbers, rational numbers, that I like to call it that, it's because it is the ratio of two integers of rational numbers is not complete. Okay, we need a Cauchy sequence. Of course, a Cauchy sequence is a sequence, such that as the terms progress, the gap between subsequent sequences between one is the value of successive sequences, yes, become closer and closer. That's exactly what a Cauchy sequence is. So we need a Cauchy sequence. It's a Cauchy sequence of rational numbers. A Cauchy sequence of rational numbers that does not converge, to a rational number. That is, it converges to an irrational number that does not converge to a rational number. Okay, so if rational numbers are numbers that can be expressed as a ratios of two integers, right? It means that an irrational number will be a number that cannot be expressed as the ratio of two integers, like things like square root of 2, square root of 3, square root of 5, or things like E, this value E, right? This value E that is approximately 2.718 and all that. So those are very good examples of irrational numbers, that is. So here we need a Cauchy sequence that have rational numbers but do not converge to a rational number. Okay, so thinking through this, there are so many examples you can take. So, but here let's take xn, which is 1 plus 1 over n raised to power n. This is one of the many examples you can take. You can take others, but let's take this. So xn equals 1 plus 1 over n raised to power n. So if we take this, right, now the first question is this a Cauchy sequence? All right. So to show xn is Cauchy, to show xn is Cauchy, right? So we need to show that for any epsilon that is greater than 0, epsilon is usually a very small number that is greater than 0, right? So there exists n, a big N, right? And that means natural number, a natural number, right? Such that n and m are greater than n, and then we can express that as xn minus xm, less than that epsilon that we have. So for what we have, right, for this expression, so we can say that for xn, which is equal to 1 plus 1 over n raised to power n, we can have absolute value of xn minus xm, and that is equal to 1 plus 1 over n raised to power n minus 1 plus 1 over m raised to power m, and all of that is less than epsilon. So, and of course, we can actually have that idea, but of course, in a way to and try to break it down further, right? So if we have the sequence xn, right? You have the sequence xn, which is 1 plus 1 over n raised to power n, from n equals 1 to infinity. What does that look like? So if you put 1, right? If you put 1, you can't start from 0, obviously, because 1 over 0 will make it indefinite. So if you start with 1, so you have 1 plus 1 over 1, that is 2 raised to power 1. So the first thing you have is 1. You have 1. And the next thing, if you go to 2, you have 1 plus 1 over 2. That is 3 over 2 raised to power 2. That is 9 over 4. If you go to 3, you have 1 over 3, right? 1 over 3 plus 1, that's 5. 1 over 3 plus 1 over. So 1 plus 1 over 3 is actually 3 over 3 plus 1 over 3. That's 4 over 3 raised to power 3. So 4 raised to power 3 is 16. 3 raised to power 3 is 4 raised to power 3, right? Is 64, 64 divided by 3 raised to power 3, which is 27. So, as these numbers progress, you can see that the values, the gap between them gets closer and closer, right? And it keeps going on like that. Okay. All right. So from all this, we can see that this expression is actually a Cauchy sequence. This sequence is actually a Cauchy sequence. Okay. So the next thing is, what does it converge to? What does it converge to? That means that, you talk about the limit of xn as n approaches infinity. That's the same thing as the limit as n goes to infinity of 1 plus 1 over n raised to power n. Now, this is a very popular expression, right? So as n approaches infinity here, you discover that this actually approaches the irrational number e, which is approximately 2.718 and all that. So you see now that though this is a sequence, now, of course, by the way, these are rational numbers, right? These are all rational numbers, but then they converge to an irrational number, okay? So, and that establishes the idea of Cauchy. So here we see that the limit of this sequence, is the irrational number, the irrational number e, which is called the Euler's number. It's called the Euler's number. Okay, it's called the Euler's number. So, I mean, all the conditions have been met. Number one, we have a Cauchy sequence because 2 and 9.4, the gap between 2 and 9.4 is smaller than the gap between 9.4, I mean 9 over 4 rather, and 64 over 27, like that. So that makes a Cauchy sequence. And then as n approaches infinity, this approaches an irrational number, 2.718. So thus, we can conclude, right? So thus, we have found a Cauchy sequence in the space of irrational numbers Q that does not converge, that does not converge to a rational number. Okay, this means Q is not complete. This means Q is not complete. This means Q is not complete. Q is not complete. Okay, that's the first part of that question. So let's take the second part of the question. The second part says that we should show that a metric space, X, P is complete. Show that it is complete if every Cauchy sequence, if every Cauchy sequence in X, P has a subsequence, which is convergent, All right. So in this case, we need to talk about subsequence and all that. So to prove, okay, to prove that a metric space XD, generally speaking, right, is complete if every Cauchy sequence in XD has a subsequence which is convergent, all right. So the first thing, let's take that. So one step can be that we say let xn be a Cauchy sequence, in X, D. Okay. Then the next thing, very important, is that by the given condition, there exists a subsequence xnk, a subsequence xnk of xn that converges in xd to some x which belongs to the space X. Okay. And lastly, we need to show that xn converges to X. Okay. All right. So to deal with this, right, let's go showing the proof. So we know that since x and k converges to X for any epsilon greater than 0, then it means that there exists a big K such that for all small k greater than big K, then the metric d of xn. Okay, well, since our metric is about P, right? So it's better I focus on that. I use the P here. So generally, the general one stated before, just for like a general metric D, XD. But here, let's focus on the P. So that for all K greater than K, the metric P, Xn, K, comma, X is less than epsilon, of course, which is necessary for a Cauchy sequence. Now, since Xn is Cauchy, for the same epsilon greater than 0, then there exists a natural number big N, a natural number N, such that for all N comma M greater than N, right? And then we have the metric P X, the metric P X N X M will surely be less than epsilon. Okay. So for all this, right, then the metric P is less than epsilon. Okay, X and XM is less than epsilon. So then can we choose? Let's choose N prime such that N prime is greater than K. So if we choose that now, then for all N greater than the maximum value between the initial N and the new N prime we have, then we can have that the metric or between Xn and X is less than epsilon. So if that is the case now, so we are simply saying that Xn is converging to X. That's what it simply means. That means that the distance between Xn and X is actually less than epsilon, and epsilon is a positive number that is greater than 0. A small number that is greater than 0. So with this now, we can say that this shows that Xn converges to X. And since Xn is an arbitrary Cauchy sequence in X, comma P, then we can say that X, comma P is complete. X, comma P is complete. In fact, of course, we have come to the end of that, but I just want to make a few comments about what I did initially. So, I mean, to make sure everything is together, so it's better we just say X, comma P up here, you know, all the while we're doing this. So it's better to say X, comma P. So to make sure we have consistency. So make sure all of that is X, comma P all the way. So instead of D, you have P. Instead of D, you have P. It's basically the same thing, shows the metric, the distance between 2 points. All right. So with this, we have come to the end of that 2-part question, questions A and B. So you want to go through this practice and be sure you master it as much as you can, and you know that way you'll be sure to be at the cutting edge. All right, so if you have not subscribed to this channel, you want to do that. You also want to hit the notification bell so you can get alerted anytime I release a new video. Of course, the other thing is you should share, you should comment, and part of the comments would be any questions you would like me to solve and all that. All right, so share with other people that may also need this, because I know there are a lot of people that are in need of things like this. See you in the next video. Thanks.